Okay, so welcome everyone. So the first talk today is given by Julie, who will talk about some different kind of proofs, because we talked about proofs yesterday, and the big problem is Tableau is a different way of defining proofs, and it's not easy to translate Tableau proofs to other kind of proofs.
Yeah, thank you. Okay, that's great. So hi, I'm Julie Cailler. I'm associate professor in the Verities team in Nancy, which is the same team as Alessio, Sophie, and Vincent, who will talk just after. So I must not take too much time. And today I will talk about a joint work with Richard, Olivier, and Johan, which is Deskolemization and how we can turn a Tableau proof into machine-checkable ones. So, a little disclaimer, I am an ATP developer, and so I developed during my PhD, and even now I developed Goéland. Can I do something? Okay, so I developed Goéland. So my days are mostly made of me asking Goéland if the thing I have is a theorem, and Goéland saying no, because there is a bug inside. So I'm sad and I try to correct it. And again, I ask, and after some bug fixing, it's a theorem now, and I'm happy. But since Goéland is my prover, I obviously don't trust it at all. And so I wanted some guarantee about my proof. And so I asked Goéland, why is it a proof? And after some time, he told me this, proof.p. And proof.p looks like that. So it's beautiful, it's TP-TP, obviously. And I'm not entirely happy with that, because if I want to check if whether the proof is correct, I have to read everything by myself, and I have no guarantee that Goéland won't do some magic at some point, which is annoying. So if I want to check that, I need to read everything, and this is not what I want. I want something more. I want more guarantee about that, and so what I decided to do is to use the fact that Goéland, contrary to most other prover which use strategy like resolution and superposition, which are more efficient, empirically speaking, to find a proof, Goéland is based on Tableaux, which is indeed less efficient to find a proof, but has the great property of being very suitable in order to output a proof. And this is actually one of the first things that Gilles told me, which is the only purpose of Tableau is their ability to produce a proof. So I decided to use this ability to make proof that can be in turn easily turned into machine-checkable ones. And in order to do this, I need sequence. So Tableau and sequence are very close to one another. They are both proof systems that work with the original formula. So no classification, no strange preprocessing, just the original formula. And they both work with a set of inference rules, which luckily are very similar. Like for every Tableau rule, we have, for almost every Tableau rule, we have an equivalent sequence rule, which is great. And the biggest difference between both systems is the purpose. Like Tableau are mostly made to search for a proof, while sequence are mostly made to represent a proof. But in practice, when you see a Tableau proof and when you see a sequence one, you can mostly read both. If you know how to read one, you can read the other one. So both systems work by refutation. They create a proof tree, and okay, in Tableau you have to start from the top and go to the bottom. From sequence, it's the opposite. You start from the bottom and then you go to the top. In Tableau, between each step, you have to write only the newly generated formula, while in sequence, you have to write everything again. This is the dots here. And in Tableau, you have some strange Greek letters in front of the connective, but otherwise it's very similar. So I have Tableau, I turn them into a GS3 proof, and once I have a GS3 proof, All I need is 100 rock file, and then I can turn my whole GS3 proof into a rock proof. And so the complete pipeline looks like that. I have Goéland, it outputs a Tableau proof, and then I turn it into a GS3 proof. I have a rock proof. And now I don't need to trust Goéland anymore because I can just trust rock. And I have much more confidence into rock. Well, it would be great, but unfortunately, it's a little bit more complicated than that. So we did the translation in rock in like 5 days, I believe. So it was quite fast. And after that, we decided to test it, like to see whether it works. And we met this formula, exists x, such that d of x implies for all y, d of y. And it looks quite nice. I mean, Goéland gave me this short proof, 4 steps. I was happy. And when we translated into GS3 and then into rock, rock told us that's not a proof. So I was a little bit confused because for me, this is a correct proof. Like I had no issue with that. So I was like, okay, another bug, fine. And I have a good news. This is a correct Tableau proof and there is no bug. So yes, less implementation for me. But the bad news is that this proof cannot be turned into a sequence proof. And this comes from the fact that when I said that we have an almost 1-1 mapping between both proof systems, well, the almost is an issue because there are Tableau rules that cannot be turned into sequence rule. And because of that, obviously, we cannot translate the rules. So to understand which rule we cannot translate, I need to introduce you to those rules. In Tableau and sequence, we have a set of inference rules, which are divided in 4 categories. So you have closure rules that allow you to close a branch, and then extension rules that allow you to extend a tree, generating 1 or 2 new branches. So for those 2, everything is fine. But then you have universal rules. For this one, in Tableau, what you do is that you use 3 variables. So here we have a Tableau, and when you have for all x, p of x, yes, universal rules are for all and not exist. So when you have for all x, p of x, you generate here a 3 variable big X, which is used as a placeholder waiting for an instantiation. And when you find an instantiation, you replace it in the proof tree and you have a proof. In sequence, since the main goal is to represent a proof, what we want is the final value of the variable already. So when I have a for all x, p of x, I generate p of a. No placeholder. Okay. And for existential rules, in Tableau, we need to introduce a fresh Skolem symbol that takes as a parameters the 3 variable of the branch. So here, yep. If I have q of y, z, and exist x, p of x, since so y with y and z 3 variables of the branch, when I skolemize, I have something like p of sco, y, and z. In sequence, since there is no 3 variable, I just generate a fresh Skolem symbol. So when I have exist x, p of x, I just generate p of c. That's good. That's great, and that works mostly. But in Skolemization, we have more advanced strategies. Those more advanced strategies usually allow us to use less 3 variable when we want to skolemize, or to sometimes reuse some previously used Skolem symbol. And those rules cannot be turned into a sequence. The very first optimization, it's called inner Skolemization or delta plus, and it allows us to use a 3 variable, only the 3 variable of the subformula. So when I have exist x, p of xy, with y and z 3 variable of the branch. When I want to skolemize here, the only 3 variable I have is big Y. So my Skolem symbol here will be only Skolem of big Y, while if I perform just normal outer skolemization, I will have to take both. These optimizations are very useful in the context of proof search because they allow you to close the branch faster and to have a smaller proof search space, which is what we want when we perform a proof search. But because of that, we cannot translate into GF3 anymore. Good thing, in outer we can translate, so that's fine. But what we want is to be able to perform more advanced Deskolemization strategy while being still able to output a proof. And this is, yes. So if I come back to my proof here, the issue was that, okay, in the first step in Tableau, when I have so not exist x d of x, I generate a free variable, big X. And later here in delta plus, I generate a fresh column symbol that only takes the free variable of the subformula, which are none here. So a new fresh column symbol, which is constant here, d of x, not d of c. And this is a Tableau proof. But in sequence, if I try to do this, what I have here is not exist x, and I want the final value of x. So here the final value is c. So I use c. I have not d of c, blah blah blah. And then here, when I want to do the Deskolemization step, what I introduced here was c. But here, C is not fresh, and the Deskolemization step in sequence require a fresh column symbol. So here, this step is not correct. I can't do that. So either I introduce something like C prime, but then I won't be able to close, or I don't use C here, but for the same reason, I won't be able to close the branch later. So my issue is that basically I try to use a column symbol before its introduction, which I can't do in sequence. And so what we try to do with Richard, Olivier, and Johan is Deskolemization, with the main idea being that we will try to perform all the Deskolemization steps before other steps, so the column symbol is necessarily fresh. In practice, we introduce the notion of formulas that depend on a column symbol, which means that this specific formula uses some column symbol. And we said that a formula F needs to be processed before another formula G, if and only if G makes use of a column symbol generated by F. So introduce your column symbol before using them. We developed a strategy based on that, which consists of taking the original Tableau proof, which can be performed with more advanced Deskolemization strategy. And as long as we don't have a delta rule or a Deskolemization step, we just copy the step as it. And when we meet a Deskolemization step, we detect which column symbol is generated. And then in the sequence, we remove all the formulas that make use of that column symbol. We apply the Deskolemization step, and then I'm sorry, that's fine, sorry. And then what we do, and then we apply the Deskolemization step, and then we replay the steps that we removed just before. But it would be clearer with an example, I believe. So this is my Tableau proof that I cannot translate in sequence yet, and I will start applying my algorithm. So at the very beginning, it's a gamma formula not exist, so I just copy it. That's great. I apply the step. I generate here this formula. No d of c implies for all y d of y. I apply it like that, so no big X in sequence, just the final value. I can do this. And then I continue. So here I take this formula, I apply an extension rule, I generate d of c, not for all y, d of y. I continue, I take this formula, and here is the problematic rule. So at this point, I know that this rule will generate c. So I look in my sequence and I retrieve all the formulas that make use of c, and I remove them. with the weakening step, which is allowed in sequence. So I said, okay, no more formula. I don't want them anymore. That's fine. And now I can just apply the rule on this formula and finally generate D of C, which is now a correct application of this rule. So that's fine. But now I want my formulas back. So I have to remember them and to just apply them back. So now I will, hey, come on. Okay, I will take this formula, apply a rule on it again, generate D of C implies for Y, D of Y, and now I can use C because C was already introduced, no more conflict. I apply again this rule on my formula, I generate D of C here, and now I can close the branch thanks to not D of C and D of C. So basically what I did is that I take the original formula, I rearrange it a bit, I remove some steps, replace them later, and everything works. Great. This example was mostly simple because we only had one branch. And when you only have one branch, everything is simple. But in practice, we often have more than one branch. And in that situation, it can become very, very difficult because you can imagine cases with a branching rule that generate two Skolem symbols in two different branches. And then when you will want to remove, to deskolemize one, you will have to replace the branching rule. So later you will have to branch again. And in the first branch, it will be fine because you are already in the good one. But for the other one, it won't fit because the Skolem symbol was in the other branch. So you will have to also do something for this Skolem symbol. So you will have to replace the branching rule again and again and again. And it's actually very easy to loop like this forever. Sometimes we also have issue with free variables that are used in two different branches, but they are not like they don't know each other because they were introduced later in both branches as the same level. And because of that, when you use one to close another branch, the strategy was a little bit lost with those one. So yeah, it's not just as easy as it looks like because of those interbranch dependencies. But what we did is that we designed with Olivier, Richard, and Johan a framework, a generic framework for deskolemization that that requires you to provide the deskolemization rule you want, and you have to specify it. And if your rule follows some conditions that we provide about being extensible and so on, the conditions are a little bit complicated, but your rule have to fulfill some conditions. And if your rule fulfills those conditions, then we prove that when they are satisfied, the rule is correct first, and then the algorithm will terminate, and your final proof will be a well-formed proof. So we designed this framework, and we implemented it, and we instantiated it in Goéland with two advanced deskolemization strategies, so delta plus and delta plus plus, and the original one. So we implemented the corresponding deskolemization strategies. We performed some experiments. So we test ourselves on the TP framework, on scene and set, on the three deskolemization strategy and deduction modular theory, which is a way of managing any kind of theory in a generic way. And we count the number of problems solved. We check the ROC output of that. And our main metric was the size of the proof in terms of number of branches. Because theoretically, when you have a proof in inner deskolemization, if you want to provide the corresponding GS3 translation, you are theoretically supposed to have an exponential increase in terms of number of branches. And between delta plus plus and delta plus, you also have an exponential. So the more optimized you are, the more exponential is the translation is supposed to be. Okay, so we count the number of the proof in terms of average and size increase. and we run that on Goéland. And what we can see is that, okay, so more advanced Deskolemization strategy provides a little increase in terms of number of problems solved, but more important, 100% of our proof were certified. So we were happy because it means that apparently we have no bug. And the average size increase is actually kind of low compared to the original theoretical bound. I believe the biggest one here is here. So with Goéland in delta plus plus, in the worst case, in our benchmark, where we have a proof that is 10 times bigger in the GF3 than in delta plus plus, but it's still way below the theoretical bound, and in average, results are quite low. So it was a very good news for us, because it means that it's usable in practice. And so what we did is we provide a generic Deskolemization framework, a soundness proof of our framework. We instantiated it into Goéland, and we provide 4 output into Proof Assistant, so ROC, LambdaPy, Lisa, and SCTP-TP. The results were promising, as 100% of our proof are certified, and it was far below the theoretical bound. Yes, and finally, if you have to remember one thing, is that it's that you can perform more advanced, you can use more advanced Deskolemization strategy in Tableaux, and still being able to produce a machine-checkable proof. And what we want to do now is to reduce the number of branches by the use of lemmas. So instead of doing things twice, we can just copy and paste some part of the proof. We would like to work on the integration of theories, and also to provide a standalone tool. So now it's just a part of Goéland, but we would like to put it apart from Goéland so anyone can use it just for the Deskolemization part. And we are also working on a framework for verification of Tableaux proof called the Tableaux ROC. So you can verify Tableaux and also some results about Tableaux themselves without having to translate everything. Thank you for your attention.
So, questions?
Yes. So you could also Deskolemize using epsilon Hilbert's operators, and it makes all, I mean, my impression when I was dealing with Deskolemization and proofs in Verity was that this made everything totally clear and simple. So
yes.
Is there, I mean, strong motivation not to do it?
Well, for using, okay, so Goéland doesn't use epsilon term yet. We thought about it once, but I wasn't sure how to do it exactly in terms of proof search for epsilon term. Well, my intuition was it was easier to deal with Deskolemization like that and to Deskolemize for me, it was simple to just Deskolemize, but I'm not sure about epsilon term. It doesn't seem that easy to implement into the proof search itself.
What you could do is to use it as an intermediate step, and so that it makes all the IDs clear, and then reprocess the proof again to introduce your terms. I don't know. I mean, when I discovered this epsilon terms, and it made my life.
Well, when we search about epsilon term, it seems like epsilon term are very great optimization. And yes, I had a feeling that everything works well with epsilon term, but on the implementation part, I wasn't sure that epsilon term would be that easy. And you have to remember a lot of things with epsilon term, and maybe it won't be that efficient in practice. So yeah.
Yes.
Do you have some data about checking time? Because you use a different output like ROC, LambdaPy, and so on.
Yes, for this one, okay. In terms of checking time, we have I believe we did some on rock, right? And it was fast, if I remember. I don't have the time in that, but it was less than 1 second or something like that. Yes, the strategy was fast. We didn't did the experiment on NumPy and Lisa yet, but I will have to do it in next month. So we will soon have some.
Okay, but the proofs are not so big. So
They are not so big. Well, it was on scene and set. Do you remember the maximal size of one proof we had back then?
Yeah, I think we had a proof with like 20,000 branches, which took forever to type check in rock.
How many branches?
But otherwise, yeah, it was pretty fast.
20,000.
Are some of those branches, because you mentioned that they are independent?
Mhm.
So probably some of those are repeated.
Oh, yeah, probably, yes.
Yes. Today I'll try to give a hint how to avoid repeating things with baby examples. Just theoretically. How to save, to log them, and to use the log memories
Yeah, it could be.
instead of computing everything again, because that will simplify everything, will make
Yeah,
it compact.
this is what
So
we
I
do.
guess that those 20,000 will go.
I have one question. So, I mean, there are complicated Deskolemization techniques, right? Where you try to scope and after. Think of on the SMT side, you have these deep Deskolemization things. And how would this work for this too, or doesn't it just? Is it just? Am I just asking something stupid because in Tableau you don't want to do this?
Well, in Tableau, the big strength of them and also a weakness is that you only take the original formula like that. You cannot reorder quantifier and so on. So I believe in this copying, you have to reorder them,
Yeah.
right? And in Tableau, you can't really do that. So unfortunately, I would say no, not applicable in that situation.
Hey, any other question? Otherwise, thank you very much.